hopefully you do have an idea what a power series is. What we're going to be looking at now is how to get that interval of convergence. So at the end of this lesson, you'll be able to find the interval of convergence of a power series. All right, so each power series does have an interval of convergence, and we talked about that before. It's a set of values of x for which the power series converges. There are three possible cases. Okay, the first case is the series only converges at one x value. So when we get through, we'll just find only one x, and the radius of convergence would be 0. The second case, the series will converge for all values of x, so no matter what you put in for x, it doesn't matter, we're going to get the series to converge. The radius of convergence would be infinity. And then case 3, which will happen most often, the series will converge for the absolute value of x minus c is less than r, and diverge if the absolute value of x minus c is greater than r. The radius of convergence is r. We will put that into English in just a second here, so you'll be able to figure out what on earth was I talking about for case 3, but that's the case that will happen most often, just like in the previous example where it converged for all x values between -1 and 1. That was case 3. All right, we will find the interval of convergence using the ratio test. So again, I really like this section because it reviews how to get the ratio test, and it actually reviews some of our other functions as well. Right, and then the last thing, very important, the endpoints of the interval must be checked individually using one of the tests of convergence from 11.1 through 11.5. So again, we're going to get some practice with our convergence and divergence rules. All right, so we're going to jump right into the examples. We're going to find the interval of convergence for the series below, state the radius of convergence. So you'll notice this is a power series because I do have a power to n, and I also have an x in my problem that can be changing. So we want to find out which values of x would make this series converge. So we're going to use the ratio test to do that, and they told us that, so I guess I'll still write that we're going to use the ratio test. I just like doing that, I guess. So we're going to have the ratio test. So if you recall for the ratio test, we're going to find the limit as n approaches infinity. This is a sub n. My a sub n plus 1 would equal 3x raised to the n plus 1. Remember that n is our variable in this problem, so we're going to have a sub n plus 1, which would be 3x to the n plus 1, divided by a sub n, which would be 3x to the n. And if I do that, you'll notice that I'd end up just getting 3x. And then if I let n approach infinity, there's no n in the problem to approach infinity, so my answer is going to be 3x. And according to the ratio test, I know that this answer has to be less than 1. Since we're not positive that this is a positive series, though, we are actually going to take the absolute value of that. So we know that the absolute value of 3x has to be less than 1 in order for the ratio test to show that there is a convergence. So what we are going to do from here is try to solve for x. The first thing that I'm going to do, because the absolute value of 3 is 3, I'm going to pull the 3 outside of my absolute values. I'm then going to divide by 3. So I'm going to get the absolute value of x is less than 1, which would mean if the absolute value of x is less than 1, we are going to get a number somewhere between -1 and +1. So I have just found my interval of convergence almost. All right, we need to figure out what would happen if I plugged in -1 and if I plugged in 1. Would that actually give me a convergent series? So what we are going to do, we're going to test the endpoints. So endpoints. So testing the endpoints when x equals -1, because that's the left endpoint. So when x equals -1, we're actually just going to plug that in and see what it would look like. So we'll get n equals 0 to infinity. If I plug in -1 for the x inside of my parentheses, I'm going to have -3 to the n power. And so that's what I'm looking at. I'm going to try to find out, does this converge or diverge? And I do notice that this is going to be a geometric series because we have a number raised to an n power. So it's a geometric series, and I notice that the ratio is -3, and since the absolute value of -3 is less than 1, we can say that this converges. Oh, excuse me. It's not less than 1, it is greater than 1. Sorry, the absolute value of -3 is bigger than 1 because that equals 3. This must diverge because we wanted to get a number that's smaller than 1. Okay, and so now I'm going to check my other endpoint. I have x equals 1 is my other endpoint. So if I plug that in for the x in the problem, if I plugged 1 in there, I'll just get 3 to the n. Since I have a number raised to an n power, this is once again a geometric series. My r in this case is going to equal 3. And since the absolute value of r is definitely greater than 1 this time, again, we will diverge. So my interval of convergence is just going to be -1 is less than x is less than 1. If I got converges for either one of those, I would have put an equal sign underneath. All right, and then to get my radius, we'll just take the right endpoint minus the left, so we'll do 1 minus -1 divided by 2. Our radius is going to be 1. All right, let's try another one. If I have n equals 1 to infinity of x minus 1 to the n over n, again, the first thing that we're going to do, this would be my a sub n. A sub n plus 1 would equal x minus 1 to the n plus 1 over n plus 1. And so I'm going to say that we'll be using the ratio test. So we'll be finding the limit as n approaches infinity of a sub n plus 1 over a sub n. And that's going to lead me to multiply by the reciprocal. And then I will get n over x minus 1. All right, so from here, I notice that I have some x minus 1s. Whoops, this should be, is this x minus 1 to the n? Yes, it was. Okay. My x minus 1 to the n's will cancel. I'll end up with x minus 1 in the numerator and then an n and n plus 1. And keep in mind that, remember, we're just treating x as a constant at this point. N is what we're letting approach infinity. So if I let n approach infinity, I'm going to get infinity over infinity. So that leads me to get to use L'Hopital's rule. And so if I do that, if I use L'Hopital's rule here, the derivative of the numerator will be x minus 1. The derivative of the denominator will be 1. So as n approaches infinity, there's nothing to plug in for n. So I'm just going to get, sorry about that, x minus 1 is my answer. And I know that this value has to be less than 1, but since I don't know if that's going to be positive or negative, we need to make sure we take the absolute value of it. All right, now you might be thinking, how do I take this and make it an interval of convergence? So what we're going to do, I'm actually going to come up here. We're going to do -1 has to be less than x minus 1, which has to be less than 1. So you can just take what's inside of the absolute value and put it in the middle. And then if I were to solve for x, we'll just add 1 to both sides. I'll get 0 is less than x is less than 2. So this is my interval of convergence. But again, I have to decide at 0 and at 2, does it converge or diverge? So do I get to include an equal sign or not? So once again, I'm going to be checking my endpoints. So we're going to let x equal 0. So if I go back up into this original problem and I let my x equal 0, okay, we'll get 0 minus 1, that's going to be -1 to the n over n. And from here, this is not a geometric series this time because that n is in the way, but I do know that this is an alternating series, so I can do my alternating series test on this one. My u sub n for an alternating series is going to be 1 over n, because remember, we just take the part of the problem that doesn't have the negative in it. So I'm going to tell that I'm trying an alternating series here. And we actually did this in the notes for an alternating series, but I'll just do it again. First of all, u sub n has to be positive. And I'll always get a positive answer no matter what I put in for n for that. So that's a check. Step 2 is u sub n. The derivative has to be negative. So the derivative of 1 over n we found before was -1 over n squared. And that will always be negative. So we got it there. And then the third one, u sub n needs to approach 0. So if I find the limit as n approaches infinity of 1 over n, I do get 0, so the third check is met. So since this is an alternating series and it meets all the tests, we know that it converges. So up at 0, I get to put an equal sign because 0 does work. Okay, and then we'll try x equals 2. If I go n equals 0 to infinity once again, whoops, actually it was 1, and I plug in 2 this time, I'll end up getting 1 to the n over n. And since 1 to the n, 1 to the second, 1 to the third, 1 to the fourth will end up being 1, I can just call this 1 over n. And then this will actually look like a p-series. So if I do a p-series on this one, p would equal 1. And since p is equal to 1, the series is going to diverge. P would have to be greater than 1 in order to converge, but since it's less than or equal to 1, it's going to diverge, so we will not include an equal sign on the 2. So that would be my interval of convergence. To get my radius again, we'll just take the two endpoints and subtract them. 2 minus 1 is 2, divided by 2, our radius is going to be 1. All right, let's try number 3. I would strongly encourage you at this point in time to try this one on your own and pause the video and come back and see how you did. All right, what I'm going to do on this one, once again, I need to, this is my a sub n. My a sub n plus 1 will equal x minus 3 to the n plus 1 over 3 to the n plus 1. So if I use the ratio test once again, we are going to do the limit as n approaches infinity of x minus 3 to the n plus 1 over 3 to the n plus 1 divided by a sub n, which will be x minus 3 to the n over 3 to the n. So I will multiply by the reciprocal. So this will be multiplied by x minus 3, whoops, excuse me, that will be multiplied by 3 to the n over x minus 3 to the n. So if I cancel some things out here, I should be left with x minus 3 in the numerator, and I should be left with just 3 on the denominator if I am right there. I think I'm right. Okay, and so from here there is no n left in the entire problem. So when I do this, that's my answer. I do know that I need the absolute value of this to be less than 1. So first thing that I'm going to do again is I'm going to pull out that 3. And then I'm going to multiply both sides by 3. So I'll get the absolute value of x minus 3 is less than 3. And then from here, I know I can write this as negative 3 is less than x minus 3, which is less than 3. So I'll add 3 to both sides, all 3 sides actually. And we'll get 0 is less than x, which is less than 6. So that's my interval of convergence. I do now need to check my endpoints to see if it's convergent at 0 or if it's convergent at 6. So we are going to test those endpoints now. So my first endpoint is x equals 0. So if I go back into my original problem and I plug in 0, I will get negative 3 to the n over 3 to the n. And I'm going to try to rewrite this to make it look like a problem that I can do. When we do this, I'm going to get, I'm going to rewrite this as negative 1 to the n. Actually, I'm not going to do that. I'm going to write it as negative 1 times 3, excuse me, I'm going to do negative 1 to the n, and then 3 to the n, and then over 3 to the n. My 3 to the n's are going to cancel out. I could have also written this, just an FYI, I could have written it of negative 3 over 3 to the n, which still gives me negative 1 to the n. We did this on the first example. I believe this was a geometric series, and since it's a geometric series, my r, the absolute value of r, is greater than or equal to 1, so this is going to diverge, which means we don't need to include 0 in our interval of convergence, so no equal sign for that one. Okay, and then we get to test x equals 6. We'll get n equals 0 to infinity. If I plug in 6, I'll get 3 to the n over 3 to the n. 3 to the n over 3 to the n is 1, and I'm going to use the nth term test on this one, because if I let finding the limit as n approaches infinity of 1, that will just equal 1 because there's no place to even plug in the n. And since I didn't get 0, I know that my series diverges. So once again, we don't need to include 6 as one of our values of convergence. And then from here, to get that radius, we will just do 6 minus 0, which is 6. We'll divide by 3. We'll divide by 2. So we'll get a radius of 3. All right. Okay, last problem. This one's a little bit different. We're going to go ahead and again use the ratio test. So we are going to, this is my a sub n. My a sub n plus 1 will equal x to the n plus 1 over n plus 1 factorial. So if I'm using the ratio test, we'll find the limit as n approaches infinity of x to the n plus 1 over n plus 1 factorial divided by a sub n. And now I get to multiply by the reciprocal of that. So multiply by n factorial over x to the n. I do know that when I do this, I'll get x in the numerator, and then down below I will end up getting, if we rewrote this out, this would be n plus 1 times n minus 1. This n times n minus 1, so everything's going to cancel out except for the n plus 1. Okay, so if I let n approach infinity, keeping in mind that x is a number, it's basically just a constant right now. If I let n approach infinity, I am going to get an answer of 0. So you will notice no matter what I plug in for x, it won't matter because I'm going to get a limit of 0, which is always less than 1. So what this means is that no matter what I pick for x, this will converge. So my radius of convergence not my radius, my interval of convergence will be negative infinity to infinity. And we don't have to check endpoints, thank goodness. So, and then my radius, if we subtract those two from each other and divide by 2, guess what? We will still get infinity. So that would be my radius. So hopefully now you can check the interval of convergence for a power series.